Button. That's done. Yeah. Whoops. So yeah, welcome to this short session on the Johnson-Lindenstrauss lemma and its applications. So I did want to start out uh, I decided it would be a nice thing to include pictures or like even just 30 seconds of like a bit of the history behind things. So I looked up the actual people, so William Johnson and Joram Lindstrauss, who made that paper. And so these guys, they're mostly doing functional analysis in Verford paper. So the actual Johnson-Lindenstrauss lemma is like a tiny lemma that they use to prove their bigger result, but it turned out to have a lot of applications. And funnily enough, like Joram Lindstrauss, he was born on like the 28th of October. So in 1 week, he would have been, uh, I mean, in 1 week, he would have had his birthday. So yeah. Anyway, so the statement of the Johnson-Lindenstrauss lemma that they proved in that paper on the bottom here, at least as a lemma for a bigger result, is that given some arbitrary epsilon greater than zero and some arbitrary set of endpoints in a d-dimensional vector space, we'll just use the RD, but in general it's not too much of an issue, we can find some integer k that is roughly the order of the logarithm of the number of points that we have in our set, and the inverse of the square of epsilon. And we can find, so we have some k, you can find a linear map from Rd to Rk, so we're going to a space of dimension k, such that the norm of that function, so the f applies, yeah, taking any points u and v in our set, the map or the norm of the distance between f of u and f of v is bounded by these terms 1 minus epsilon and 1 plus epsilon times the norm of u minus v in the original space. And so what that means is that if we take like epsilon's very small and close to zero, this basically says that the function, the linear map f, does not distort the length or the distances between the points in v too much. And this is very useful for a number of applications. So yeah, so for some actual practical uses, well, it's very nice because if k is smaller than d, we can lower the dimension of our set. For example, if we want to do nearest neighbor search and we have like a very large dimensional data set, apply the Johnson-Lindenstrauss lemma by using one of those transforms, and boop, you have a lower dimensional subspace, and so it's cheaper to do. So any kind of like algorithm that depends on distances between pairs of points is going to be improved like that. So nearest neighbor, clustering, stuff like outlier detection, and also numerical linear algebra, so low-rank approximation, regression. So just a bunch of things where it's useful to lower your dimension in some way. And you can use this for stuff like differential privacy and graph embeddings. So yeah, like you have a graph and you want to embed the vertices of a graph inside dimensional space such that it's embedded and you'd like it to have the lowest dimensional possible subspace, and you can do that with Johnson-Lindstrom. So generally, I guess the person who shared this isn't here for this, but this paper by Frexen is a very nice resource because it lists all the results and all links. So it's a good starting point if you want to learn more. So yeah, I'll just briefly cover the proof or a proof of the Johnson-Lindström lemma. So the actual proof that is in the original paper by Johnson-Lindenstrauss is, as always in this case, very complicated and long, but people have been like improving and simplifying the proof. So this is one is from this paper by Dasgupta and Gupta, and it's similar to other proofs that we can find. So the rough idea is that like given some arbitrary vector v in Rd, we can consider its projection on some random k-dimensional subspace. We'll see just a bit later what a random k-dimensional subspace means, but if we take some arbitrary vector and then project it down to some arbitrary random space, then the length of that projection has an expected value, mu is equal to k over d. Roughly, the idea is that if you assume that, okay, v is fixed, and then you take some arbitrary subspace, you're roughly taking about 4k over d% of the norm of it. Some other proofs, they actually flip things around. They assume that your subspace is fixed, but then the vector is like randomly distributed, for example, using a Gaussian. It's actually both of these methods are actually equivalent. And so it's sort of the idea that if you take a random vector of like Gaussians and chop off like d minus k coordinates, then your norm should be roughly k over d, or the squared norm. And so this is the expected value of the length. And actually, like if you imagine that this is just a Gaussian vector, then the square of so the sum of the square of coordinates it's so a sum of the square of Gaussians, and so it's a chi-square distribution. And there's some nice results about that because it's what's called so concentrated around its mean. So roughly, so these are some very standard probabilistic argument. L is concentrated around its mean, so this mu. That is, if we take some beta smaller than 1, for example, the probability that L is smaller than beta times k over d, and we'll use that to get our bounds, then it's smaller than this exponential that depends on k and then 1 minus beta and the logarithm of beta. And then if beta is greater than 1, then we have essentially the same thing. And so this is just a lemma. If you want the proof of that lemma, I refer to this. It's a very nice and clear proof. So we can use this to actually prove the main lemma. So first of all, if d is smaller than k, so we're trying to project to a larger space, then obviously we can just project and we don't need to worry about it. The interesting part is of course is k smaller than d. Then again we take a random k-dimensional subspace. We'll go that we see what that means later. So take a k-dimensional random subspace and then let v prime I be the projection of vi. So vi's are the points in v, and we project each one of them into our subspace S. And then if we apply the previous lemma to the norm between, so L is the norm between the projection of vi and vj squared, and we take mu being the expected value of that, then we get that the probability that this squared length, is smaller than 1 minus epsilon mu, and we apply the lemma that we have on the slide before, and if we do some manipulations, a lot of these basically involve standard properties of the logarithm and so on. We end up that this probability is smaller than 1 over n squared. And similarly for the other side, like the probability that L is greater than 1 plus epsilon mu, it's also smaller than 1 over n squared. So that's nice because
This is probably a
I,
stupid question, but is the norm the same as a
yeah,
dot product?
go on. In this case, the norm is a dot product. Yes, it's the Euclidean norm,
That makes this a Hilbert space.
indeed. Although I think there are some, so yeah, generally it's for Euclidean space or Hilbert spaces. So technically Hilbert space is a bit more technical. Although there are some applications of the JL lemma for if you want to project into the L1 space, for example.
Do the technicalities around a Hilbert space have to do with infinities? And you're a computer scientist, right?
No, I'm a mathematician, so I do know the difference between a Hilbert space and a just Euclidean space.
I probably don't.
Yeah, it's fine. The difference is that a Hilbert space can have infinitely many dimensions, and then the Hilbert part means that it's a in a product space, but it's also what's called topologically complete, which means that if you have a sequence that looks like it should converge using like the Cauchy criterion, and it
Caution.
does converge. So it's a more subtle thing. It's about the topology.
Are you a caution fan?
Sorry?
You're French.
Uh, Close, Belgian,
Oh, okay. But they speak French in Belgium.
indeed. Anyway, I guess today is not the topic of Hilbert spaces or French-speaking Belgian, so we'll move on. So yeah, roughly we get this nice result that the probability that L is greater than 1 plus epsilon mu and smaller than 1 minus epsilon mu is both bounded by 1 over n squared. And so if we define our linear map for Johnson-Lindenstrauss map by f of vi being simply vi prime, then we also scale it by the square root of d over k. And then we have for that for any pair ij, the probability that f of vi minus f of vj is not within that space interval where the distortion is nice, so we're beyond, so we have a distortion greater than 1 minus epsilon or 1 plus epsilon. Why? Because it's the probability that we're both below that interval and above that interval. This is at most 2 over n squared by what we said earlier. And that means that the probability that any pair of points in V, so we have to take any two pair of points, the rough idea, right, is it's the probability of the union that of this happening for all pairs of points, and so we can bound it by just the sum of all these probabilities, and that way we get this. So choose two among n times 2 over n squared, and this turns out to be equal to 1 minus 1 over n. And this is really nice because it means that the probability that that no point has this happen, that is, f has the probability that we wanted for the theorem, f satisfies this probability with probability at least 1 over n. So from that, we basically are lucky enough. And so that's the end of the proof. So going back to what projecting into a random subspace means, roughly, so a random subspace, you could think of it as taking a random basis of, or a random set of vectors that are um, linearly independent. So roughly, let's assume that we just take an orthonormal basis because we can of Rk uniformly. And the uniformly, so there's a nice thing about um, like sets of orthonormal basis or sets of k orthonormal vectors in RD, in that they form a nice, so I guess differential manifold, and it's a differential manifold that is compact, so it has a nice measure that allows you to sample uniformly from it. So it's a bit
Is
more
this about transformer architecture?
not necessarily, I don't think.
Okay.
At least I haven't heard this apply to transformers, but so yeah, so just saying this is the math reading group and we're talking about the Johnson-Lindenstrauss lemma, so not necessarily transformers. Anyway, so if we want to sample like a random, go on.
Oh, nothing. I was saying I understood.
Okay, cool. So yeah, to sample a random subspace, we can sample a random orthogonal basis, and mathematically this can be done by sampling from the what's called the Hauer measure on the Stiefel manifold. Don't worry if this goes over your head. Basically, we need to sample a random d times d orthogonal matrix and discard the last d minus k rows. That's fine. Um, Numerically, we can actually do that by sampling a d times k matrix A with independent Gaussian, so standard Gaussian entries, and then we take the QR decomposition of that matrix. Then there's this nice theorem called, I think, Bartlett's decomposition theorem that says that the rows of Q, they are on a orthogonal basis of a random k-dimensional subspace of Rd. And so then we can just take the transpose and that that works out. Now, we'll see later that actually this, whoops, yeah, this. So we'll see later that actually like this whole thing of taking the QR decomposition is very expensive. Like computing the QR decomposition of a matrix is generally O n cubed, so a bit too expensive for what we'd like to do. And it turns out you don't actually even need to compute this like orthonormal matrices. Is just taking this matrix of IID normals is enough. So a nice little corollary. So that one is in the the fraction paper, is that we can also preserve the inner products. So we can not only preserve the norms, but also the angles between the points in V. So we'll take D, epsilon, V, and F as defined previously. And then if minus V is in the set for any U V, then this inner product, so f of inner product f of u, f of v minus the inner product u times u and v is bounded by this epsilon times the product of the norms of u and v. And so in practice, that means that if we want to preserve the inner products as well, just add the negations of every vector in our set to the set, and then compute the Johnson-Lindenstrauss transform, and we also get the inner products preserved, at least in this way.
Does this make it a group or a ring, or what does this do?
It just makes it a set, or I guess you could call it a symmetric set because for um, and it's negative, it's also there, but then there's no just a set, so there's not necessarily any operations. Okay, cool. Let's move on. So yeah, last slide. I told you this would be fast. So there are a bunch of improvements. So if you want more, I refer to the Fraxon paper, but so like the original paper by Johnson and Lindenstrauss, they only prove that k, so the dimension that we can reduce is about the order of 1 over epsilon squared times the logarithm of the number of points. But then a few years later by Frankel and Maehara, they showed that a nice bound, and that's basically the bound that most people use in practice, is this one where you have essentially epsilon squared minus something of the epsilon cubed times the logarithm of the number of points. And in general, that's enough. But I think there's a bunch of results that get you a little better depending on some conditions. But that's yeah. Read the review if you want more about that. But more, I guess, more interesting is like constructing the actual transform. Sorry, we've seen how to like sample a random projection on the k-dimensional subspace, but we can maybe do a little bit better. So a nice result by Indik and Motwani, they show that actually you could use just use a matrix of IID Gaussians, no QR decomposition needed, and use that as your projection matrix, quote unquote, and that's also fine. At least it works reasonably well, and this type is what's generally known as like a random projection in the literature. So I guess I haven't talked too much about random projection, but they're one of the major applications of the JL lemma, and you can use it as sort of a feature transform. Um, so, okay, you can use Gaussians. That's nice, but you need a dense matrix of like floats, so it's a bit too expensive. Turns out you don't even need Gaussians. So this later paper by Arriaga and Vepala, they showed that you can just use a matrix with random entries in minus 1, 1, just like flip a coin, and that also works. So that's nice because you only need integers and you can do a bunch of stuff. And then Aklioptas, a bit later, he showed that you can improve that a little bit by having a sort of sparse matrix. So he showed that you can use a matrix also with IID entries, but then with the probability of getting 0 being 2/3, and then the probability of getting either minus 1 or 1 is 1/6. So that means that 1/3 or only 1/3 of your entries are non-zero. And so his argument that if you want to do the Johnson-Lindenstrauss transform for like in a database with a very large dimensions, then this helps you shave a little bit of compute time. Then there's a whole bunch of improvements and different stuff, but I had literally no time to add more to these slides. So yeah, that's the
That
end.
was amazing.
Okay, any questions?
So, well, I got in late. What is the topic actually?
We are talking about the Johnson-Lindenstrauss lemma and its applications. So basically, this whole thing is about this sort of mini session about the Johnson-Lindenstrauss lemma. So it's basically saying this: for any sets, so take epsilon greater than 0, take endpoints in Rd, and then you can project down the set of V to some lower dimensional subspace such that the distances are roughly preserved.
I think I understand most of them. Yeah, that's interesting. So, what are the applications?
Well, glad you asked. So I guess we do go over the slides, but yeah, the nice thing, if you can project like a data set and the distances are preserved, it means you can sort of shave a bit of dimension. So for example, let's say you want to compute the like a KNN or something, or the nearest neighbor search.
Hmm,
Nearest neighbors, like the complexity of that depends on the dimension of your space. I think it's roughly polynomial or something. So
sure.
if you lower the dimension, that makes it a bit less expensive.
And the O is a computer science thing, though. That's like compute time.
Yeah. I mean, it's the same notation in general. Like it's yeah the order or yeah yeah polynomial in compute time, I think.
I heard of a convex optimization thing in robotics that was supposed to be groundbreaking from Ted Drake, an MIT roboticist. Convex sets, and it was going to do like path
Using
optimization.
the JL lemma or
No idea.
huh? But yeah. I mean, convex optimization is like a very large topic. It's like I think in the review they mentioned stuff um, like discrete problems where you have integer values and you want to optimize over that, and somehow we can use that a little bit.
Is the JL lemma really new?
No. It's like, I mean, the original lemma is like 1984.
Okay.
I
I've
mean,
never
I'll
heard of it before.
and point out a couple of things regarding the Johnson-Lindenstrauss and the JLMA that I found pretty interesting in my notes, and it's somewhat random. It might give you a bit more insight as to why we might want to use it or where it's useful. So, anytime we're dealing with large dimensional spaces, things get weird. It's like there's a lot of non-intuitive properties of the large dimensional spaces, and that was a part that I found fascinating. Was I didn't for so many, for so long you picture 1D, 2D, 3D, you can get a pretty good sense intuitively of those. But once you get into high dimensions, things get very strange. So you get things like the concentration of measure, and the fact we can actually use that, and combining that with the union bound to to, to prove this lemma in a fairly straightforward fashion is incredibly useful. A couple things though that are the drawbacks or the pros and cons regarding the Johnson-Lindenstrauss is that it's both a pro in that it's linear and oblivious, so that you can apply it almost everywhere. But the fact that it is linear and oblivious leaves out a lot of the more deeper interactions. So it's useful as something for a sort of brute force dimensionality reduction, a pre-processing step, but not so much in terms of getting insight into the actual data itself
Yeah,
is what one of the main takeaways that I came away with.
Is it a little bit like how Word to Vec was useful, but it leaves a lot of the structure on the table? You're never going to recover it.
Yeah, I'd say so. That makes sense. I mean, anytime we're embedding into we're preserving the pairwise interactions when we're embedding into the smaller space. And at least that's what I take away from it. And again, correct me in any mathematical sense where I go wrong here, because it's just I'm just trying to just convey basic intuition that I have, and so it's not from any kind of rigor at all. Um, but any time we're dealing with, again, huge dimensional spaces, it becomes intractable to actually work with in its raw form. So almost always we're going to embed down into a lower dimensional space. The JL lemma just gives us first of all some mathematical backing, but the actual application of it gives us ability to, without having to understand a lot of, we don't have much inductive prior. We don't have to know about it a lot in advance. We can take a point set, we can project that down into a lower dimensional space and work with that in a more tractable fashion. So when we want to do things like K and N, which is very intractable in its raw form, we're projecting it down to a much smaller space, and we can get sometimes, is it actually an exponential reduction or is it just a polynomial reduction? It is log n in the number of dimensions, is it not?
So yeah, you get about log n in the number of dimensions, but then there's a 1 over epsilon squared term that might make
Right.
things a little bit
That's the
more
constraint.
complicated. But I guess if you
Okay.
pick epsilon, it's constant, so yeah, logarithmic. So the thing is that
And
I
I
don't
think
even
that
know.
epsilon choice is fairly, that is actually fairly a generous choice, is it not? It's a loose constraint in that it's fairly easy to meet that constraint.
I mean, I guess having this roughly logarithmic rate is probably as good as you could hope for. Like, if you told me, oh yeah, you can boil down your data sets to like O log n and preserve the distance, I think I'd be pretty happy.
Exactly. Which is why
by
it's
by
so
choosing
useful.
epsilon constant or something like that.
Yeah, if you pick epsilon to be a constant, then it's just yeah, some constant factor times the log n. So
And my point was that that constant factor is it's not a it's, where is the actual the that factor itself? When I saw it, it's not that it's a very hard constraint. In that, when I mean that it's not a hard constraint, it's. I'll post it when I in the math reading group. What I'll do is I'll post a couple of the references that gives a better explanation, and me trying to do it off the cuff. Specifically,
Hard constraint. You meant it's not difficult to meet, not
yes,
that
I
you're
mean
going to
like
have to
that.
live by it.
Yes,
You'll have to live by it, and then it's a hard constraint in that sense.
in that it's, you're not going to bump up against that constraint very easily in normal practice. Is what I'm trying to say.
Okay.
The Johnson lemma, the JL lemma itself is pretty straightforward. The application is pretty straightforward. I think the the actual implications in the underlying the usefulness of it is actually a gift to us from in a sense that it's almost like a free lunch.
yeah, it
The
feels
free
like
lunch
so.
is actually, go ahead.
It feels like one, yeah.
Yeah, it feels like one, although hidden underneath that is the fact that it is a linear transform and it is oblivious, so we do miss a lot of the interactions in the data itself. And in that case, then I see it almost like as a precursor to more advanced decompositions and such, and more that take the structure of the data into account. Like, even like the low rank approximations would sort of be my next step up from here. Would that be a
Yeah,
correct
yeah,
assumption?
true. But actually, the if you go to like Frexen, he mentioned that sometimes people use like a random projection before doing PCA. Like he has a little section talking about yeah, PCA and like random projection to do two different things, but sometimes it's nice to combine the two.
Right.
But I
So
guess the
even
fact that
PCA is a little bit more. It takes more of the data into account than this is almost like like your basic hammer to start with.
yeah, but it's nice enough. Like sometimes you really don't just only care about the distances and you don't really care about anything else. Like for example, I like the idea of graph embeddings with this, like because I
Hmm.
mostly like work with in not quite graph but network theory. So like being able to embed a graph and having that in a low dimension, to me that's nice enough, and I'm be happy, but trying to come up with things.
Is this what they call geometric AI? I was reading in Nature, like, what will become of science? And they mentioned geometric.
I don't think so.
Come again?
It was some article in Nature about like what will become of science as AI advances, and it used the phrase geometric AI, and it seemed when I looked it up to have something to do with just
Yeah,
I don't know graph
I
embeddings in
think you keep
particular,
cutting
but
off like right after geometric, and so I can't hear the second word.
AI.
Geometric AI. Yeah, I
I
have
would
never heard of that.
imagine, yeah,
I
I
don't know what
imagine
that
he's
means.
probably thinking of he may be thinking of geometric deep learning, which is probably what has gotten the most buzz in the press and such. And that's not really the same thing here.
Yeah,
That's probably what it actually said. That's probably what it actually.
yeah, no,
This is a particular lemma which allows us to utilize it to practically make a transform, which allows us to transform data in a way that we can do a thing called sketching, which makes it a lot easier for us to deal with large multidimensional data sets.
Where does
Somewhat
Topos
different than geometric deep learning.
theory figure into all this?
so sorry, come again?
Where does like Topos theory and Grothendieck? You're Belgium, you know
Yeah,
Grothendieck.
sure.
Where does that figure into all
I'd
this?
say you're probably trolling at this point.
Yeah,
Yeah, dude's trolling.
I'm not. I just don't. Look, I'm casually interested in math. I don't know a lot of it.
yeah. I mean,
Well, if you were casually
Grothendieck
interested,
is like
that's great.
very, very far away from this.
You're dropping into a conversation that's on a specific topic and throwing out random. I don't know what color is the sky today, and it doesn't really matter. It's not really relevant to the topic at hand.
You probably raise a good point. Okay, I'm gonna try to know
Probably.
my lane here.
Anyway, yeah. Do we have any other comments or questions? I guess not. So yeah, thank you for both for and everyone for the discussion. That was really nice. Like I didn't know too much about the JL lemma. I mean, I knew its statement, but I hadn't seen it before, so it was nice to like dig into it a little bit, although I was a bit
That's
pressed for time.
pretty cool rabbit hole. I like it.
Yeah,
Fun.
definitely. I have a new folder in my heap of PDFs with JL lemma on it. Yeah, thank you
Yeah,
for suggesting it.
and Gremlin guy, if you got a topic at hand, just throw it out to the reading group, and I mean, genetics Satan, he knows a ton of stuff. He'll do a presentation on it. he'll,
I mean,
he'll,
sometimes I present
people know
stuff and
more.
I don't know about it.
That's the best part. That's the best way is to learn it. The best is try to teach it because there's nothing like the embarrassment of getting it wrong in front of a bunch of people to make you motivate you to go back and learn it better.
Right? I bet that's true. I I'm obsessing over this movie review of Oppenheimer, but they said Oppenheimer said things we don't understand we explain to each other, and I was like, that's a brilliant statement.
Yeah, but see, then there's the statement by John von Neumann saying, okay, in mathematics you don't understand things, you get used to them.
Yeah, I love that one too. That's a really you never understand math, you just get used to it.
Yeah, there's a bunch of von Neumann has a bunch of really nice quotes. But anyway, yeah, thank you all for the discussion and the attending actually. So I think so next week we won't have a session because I'm really pressed for time, but then I guess in 2 weeks we can do something. So either we read one of the papers about RMT, so random matrix theory applied to machine learning. I think I saw a nice one that uses like basic Wigner matrices, so that might be nice.
Did you say random matrix something?
Random matrix theory, which is a topic we've covered a little bit before.
That's similar to how you said you could just choose random -1 or 1 in a matrix and it would still give
It
an
is
okay
related, yeah.
result?
Although random breakthrough tree is about like the eigenvalues of such matrices. So you take a matrix with random entries and then you ask what is the distribution of the eigenvalues.
That's cool. You know, I used to really stress over whether linear algebra even had applications. I was such an idiot.
It has all the applications.
I know, right?
Anyway, so I think we can leave it at that. So yeah, thanks everyone and see you guys